Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for this month's installment of Thirsty Thursday and the last one of 2020. Please take note of a few of the dates, upcoming events listed on the screen. Notably, our first Thirsty Thursday of 2021 will occur on January 21st. Glassbuild Connect is still open, but just for 3 more weeks. Be sure to take one final tour of more than 70 educational presentations, including the recording of this presentation on demand, plus products and services from 300 and more exhibiting companies at glassbuild.com. The next Glassbuild America is planned for September 13th to 15th at the Georgia World Congress Center in Atlanta. Registration for the NGA Glass Conference is officially open. We hope you'll join us on February 9th for 2 sessions that will look at the future implications of the latest codes and standards developments, plus a unique perspective from the General Services Administration. We will address questions at the end of the presentation, but feel free to submit them using the Q&A feature in your toolbar at any time. I'm now pleased to introduce our speaker, Julia Schimmelpenny. She's the Architectural Industry Technical Manager for the Advanced Material Interlayer business of Eastman Chemical Company. She has more than 30 years experience in lamination and laminated glass application support. She provides technical product support to glass fabricators, architects, designers, engineers, and specifiers. Her work includes new product development, qualification and commercialization of laminated glazing solutions, regulatory development, and industry education and association support. Julia also manages the Americas Customer Applications and Support Laboratories in Springfield, Massachusetts, and Sao Paulo, Brazil. Julia is a very active contributor in the glazing industry, being a member of ANSI, ASTM, CGSB, ISO, GICC, NGA, and other organizations. Julia recently received the highest award given by ASTM International for her contributions to the industry and by being designated an honorary fellow. She's also a past recipient of the prestigious C.G. Carney Legacy Award given by the National Glass Association. Julia, welcome.
Thank you, Sarah, and welcome to everybody. Thanks for taking the time to come for the Thirsty Thursday. We're going to delve into acoustics today. The session will address occupants' demands for noise-related control and comfort and how it relates to glazing. What we'll try to get out of the session today is discovering why paying attention to noise is important, clarifying some of the basics of acoustics and how glazing can impact those characteristics, summarizing the applicable testing without hopefully putting you to sleep, and then discussing and illustrating some contemporary uses of acoustic glazing and design. So the first question is always why acoustics? And what we have to look at when we look at acoustics is to look at what the macro trend of urbanization is doing. And you'll see in this that on the left-hand side, we have a picture on the top of Las Vegas in 1920s and then Las Vegas today. And so when you look at that information and you look at that, you'll see that the trends of urbanization are really incredible and having a major impact on us. Population density is increasing. 90% of our population live in 10% of the land, typically coastal communities, and we're living and working closer together. So all of that does have a play on the landscape that we're using as well. The built environment is changing. We have existing footprints are being recommissioned from a small, potentially just a parking lot into a very high-rise hotel. We have closer proximity of the buildings and taller buildings. Therefore, the noise can tend to reverberate in those areas and before it goes up and out. We're looking at houses and offices closer to transportation than it's ever been because we're trying to consume and use that land in the most appropriate manner. And we're also spending a lot more time indoors. About 90% of our time on average is spent indoors. And because of that, we have to be concerned about the effects of noise. So the other part of it is that we see modern designs using a liberal amount of glass. And historically, that has been a weak link for noise. And we have to keep that in mind as we go through this session, because we're going to come back to it at the end. So why noise? Well, the World Health Organization has designated noise as one of the top 3 pollutants in the world. And so it may not be seen. We might not see it on the ground littering or looking up in the sky as smog, but it's certainly there, and we can hear it. And it does disturb many facets of our life in the way of communication and comfort and concentration. And concentration is a big one because that has an impact on safety, it has an impact on job performance, and more importantly, on our individual health. The other key is the sources of noise are increasing. So just a quick look at this chart and you can see what happens with noise in different applications. In a bedroom or a hotel area, you can have sleep disturbance, and we don't have to go into all the factors of what poor sleeping has on our health. In classrooms, this is a major concern because you have speech interference and therefore learning interference. And there's been proven in many documents. All you have to do is Google it, and you'll see that noise has a very, very direct implication on students' capability to learn. And during the COVID pandemic, anybody that has had children trying to learn at home, nephews, nieces, grandkids, or even trying to work at home with the different noises, you'll understand how hard that is to adjust to. Healthcare is another area where recovering and resting time certainly have very, very significant impact by the amount of noise. It's been proven that the quieter it is, the faster recovery is in healthcare areas. Office areas, worker performance, and attention span is very critical. And meeting rooms, the intelligibility of the speech, can you understand, can you clearly hear what's going on, and the attention span of the attendees are also very, very critical. So the adverse effects of noise are also something to be aware of. We all understand noise and the loss of hearing. About 10% of the population today is hearing impaired at a very early age. It is getting worse as the noise is increasing. But the bigger part that is of concern is the psychological and physiological areas. Noise can lead to everything from anxiousness and depression into some of the things we've already talked about. Concentration, lack of focus, a decreased ability to read and comprehend. Self-motivation is also one of the issues with a lot of noise, and learned helplessness. This is especially apparent in schools where if they can't hear, the kids give up. And it's a learned helplessness that the minute the noise level gets high, they just resign themselves to not being able to do anything. And then sleep, and then the recovery time. So when we look at our design dilemma and we look at noise, we know that we need buildings. It's a human need to have shelter, any kind of shelter. So that is a need that we all have. We want a lot of daylight. We like to connect with the natural side of things. And all of this gets into the liberal use of glass and the willingness for us to use glass to bring natural daylighting inside for not only energy, but also for the psychological reasons. But what we absolutely need is quiet. We must have some quiet for us to sleep, to turn down, to turn off, and to rejuvenate, and in some cases recharge our batteries. And so we have to find ways to combine all of this so that we can function at our highest levels. And so that's when we come to sound abatement glazing. In the sound abatement glazing, we see that the specifications are tremendously increasing. It is driven by choice or municipal mandate. So you don't really see a noise abatement standard written in hard text in a building code. Now, cities and other municipalities may have noise regulations, and there isn't a state in the continental United States that doesn't have some location within it that doesn't have sound control requirements. So it really, really is growing. There are noise requirements in some of the health, safety, and wellness regulations. So in LEED, you can get points in well building design and things like that. They do give noise abatement points and credits. You also have to look at the building type, the location, and the use. If it is a greenhouse that's in the middle of nowhere and it has very low occupancy, it probably doesn't have a need to have acoustical comfort inside. Although, I've not done a study to see if the plants really, would grow better and produce more with certain types of noise or lower level of noise. But the building type, the location, and the use of the building is very, very critical. The other key is you cannot move the building. So once the building is up, what gets built around it is a secondary. And so a lot of times you'll figure, oh, it's a pretty quiet area. We're okay. We don't need noise. And think of that on a housing, a residential side, and also on a growing city. But you don't really have a lot of control of what goes up around you in most cases, unless you own acreage around the facility. And so that's also a critical factor. The other hard part with sound abatement is the perception of the noise, and the acceptability of the noise limits differs by individual. I like to tell the story here that Greg Carney and I were at a conference, and we were in San Diego, and our hotel was near the airport. And I had a room looking over right where the planes were coming in. And Greg was on the other side of the building, but looking at that same spot. And we got down to meet with a bunch of industry folks. And Greg says, "Oh my God, my room is awful." And I was like, "Well, what's the matter with it?" I said, "Did you go down to the front desk and talk to them about it?" He goes, "Well, there's nothing they can do. It's those darn planes. They're coming in for a landing all the time. It's driving me crazy." And I kind of chuckled at him. I said, "It's really funny because I was going to say, I have a great room. I'm right at the landing strip and I can hear the planes coming in." So being a pilot, I loved it. He didn't. And that's the big difference you have in perception and acceptability with this product characteristic. And you have to keep that in mind. The other part is we are demanding comfort, and it's not just in acoustic, but it's in thermal comfort and all different areas. So we're demanding that glass is multifunctional, and you have to bring those functionalities into the glass in more ways than one. So back in the day, if we looked at our teepee that we had, it might have been okay to have a piece of glass to keep the insects out or the water out. But today we're certainly asking glass to do a lot more. So the main products in sound abatement that we look at under this are going to be laminated glass and insulating glass configurations. Those are the two things that are typically used. Now, that doesn't mean that those are the only two things, but those are the two things we're going to concentrate on here because they are the most widely used materials. So let's get into the basics of acoustics. And I promise you, this will not be a physics lesson. But we do have to get into a little bit of this by going forward and taking a look at what is sound. So sound is molecules in motion. It's a mechanical wave. It has to go through a medium for transmission, and that medium in most cases is air, water, or a solid object. For us talking about acoustic, it's solid objects and air mostly. Certainly you could put this in an aquarium or something like that, and that changes those dynamics. But we're mostly talking here about solid objects, which is the glass and air. We do measure sound level by pressure, and that pressure is called a decibel, and it's designated as a small d and a capital B. You will sometimes see that as dBA with a capital A at the end of it. That means it is weighted for human hearing. dB and dBA, as confusing as it may be, are really used very interchangeably in our industry, but just note there is definitely a difference between the two of them. So any vibrating object at all will generate an acoustic wave. and that wave will propagate through the medium, be it the air or through the solid. And that's how we hear. Those frequencies, they come through. They're called hertz. There is the name of them. They'll come through and they actually vibrate our eardrum, and that's and move around the little hairs in our ear, and that's how we hear. Now, those frequencies are grouped in octaves, and it's a grouping of a series of frequencies. Think of a piano. You have octaves on a piano. So these are grouped in octaves too. And we read these frequencies in 1/3 octave bands. And so those keys on the piano are broken up into thirds. And we take readings at those levels. There's also this thing called a critical frequency. And this is when the bending of the wave matches that of the material it's going through. And it's called the critical frequency because the sound waves do not have a lot of difficulty going through a medium like that. Glass has a critical frequency. That critical frequency changes with the thickness, and we'll look at that. So there is a spot in all glass, all units, that the sounds will come through easier than other frequencies. And again, that does change with the thickness of the glass. The key, though, is by using techniques and mechanism, that vibration and those waves can be damped, meaning we can make them smaller. And so this diagram on the side, if you take a look at the diagram, you can see it's a tuning fork. And if you hit a tuning fork, you know it starts vibrating and you can hear a certain pitch. Well, that creates those waves. And you can see at the top of that our air molecules are nicely stacked, very uniform. Well, as soon as the wave hits, it starts pushing around those molecules, and that's the medium changing, and that's what's coming to meet our ear. The damping is caused when you try to stop that. And so you can dissipate that vibratory motion. It changes to heat energy. Now, this doesn't mean that if you grab a tuning fork, your hand is going to burn unless you've put it in an oven beforehand. But it just means that, energy cannot be created or destroyed. It can only be changed. And so the sound energy is changing to heat energy. Materials have an inherent amount of damping. And we gauge that by how long the sound will persist. So a tuning fork is made to persist, so it has low damping. When you bang a tuning fork and you put it up to your ear, you can listen to that sound for quite some time. However, think about if you put your hand around it. It stops almost immediately. The same thing with a bell. If you ring a bell and it's loud and you just grab it, it stops. The sound stops. And so that's what damping does. Glass itself has a very low damping, meaning the sound will persist or the sound will go through it. Higher damping materials will increase sound isolation, meaning it'll help stop the sound and the progression of sound. It will increase sound transmission loss, which is a good thing. You're trying to reduce the amount of sound that's coming through, and therefore you get greater sound reduction. So that is all I'm going to go through in the acoustics part of it. There are encyclopedias more of information that we could go through and dive into. But for what we're going to do today, this is really the basis of what we need to know. So what I'd like to do now is go through the methods of test. So we have these principles, but how do we test glass, or how do we test materials to understand the acoustic performance of them? So the first thing is a product evaluation. So most construction products can be tested for acoustical performance. They just need to use a standard practice, and there's several different standard practices out there. The first one that was written down and documented for international use came from ASTM. It's still around today. It's ASTM E90. And we'll talk a little bit more about how that's done. But typically glass and glazing is evaluated by the same method. and you use sensors, and you use sound generators and everything else. You can test the glazing alone, or you can test it in a system. You will get two different results depending on how you test it. It's like anything else. If you're testing a component and you put it together in a system, you have to make sure the whole system works together. And the component can bring a lot of very natural and nice characteristics to it. However, you're going to always be governed by the weakest part of that system. So the testing itself is done in a very simple to understand way. You have a receiving room and a source room, and in the middle of that room is where you put your sample. So you start generating noise on one side and you measure the sound level, the pressure levels at the frequencies. It goes through the material you're testing. In this case, it looks like it's a piece of glass. It could be a window system. It could be a car door. It could be a concrete wall, whatever. But it goes from one side, the source room, and you measure how much sound doesn't get through that opening with your sample in it in the receiving room. And that is called the sound transmission loss number. The methods that you use, there's two different methods that use this same dual room with a demising wall structure. One is ASTM E90, which was created around the early 60s, 1960s. It's been the standard test method for laboratory measurement of airborne sound for since then. Not too long ago, ISO came out with their test method, which is ISO 10140, uses the same principles, but does have a few differences in that they fix their sizes to a very specific size, and they don't account for spikes and dips the same way E90 does on the calculation. But overall, the method of test is the same. There is one other test that's used for glazing measurement, and this is a mechanical impedance test. It is specific for laminated glass. It's done on a very, very small sample, and it just characterizes the components, so the glass and the interlayer. But it is an important test to remember. So once we do this test, what we do is we get the test data. And you can see on the chart that we have a whole bunch of red dots, and those are correlated with the frequencies that are along the x-axis of this table. And so those are the frequencies we test at. So you're going to test at 80 hertz, 200 hertz, 1000 hertz, and so on. And you test at each one of those 19 measurement points along that x-axis. And then you plot it to how much sound is lost from the source room through the receiving room. And from that, you get your sound transmission loss graph. And in this graph, it's very clear to see that we have a critical frequency dip. And that's that dip where you will see that the sound is getting through easier. Normally, you would think that this would be flattened, but it isn't, because that's where the bending and the wavelength are very similar. So it does encompass the peak human hearing. It typically runs from 80 hertz to 5000 hertz when you do the test. There are some labs that have the capability of running lower and some that run higher, but typically you don't see data much higher than 5000 to 8000 hertz from this stuff. The human hearing peak is between 2000 and 4000 hertz. However, we hear from 20 hertz to 20,000 hertz. That changes for each individual. It's different depending on gender. It's different depending on age. It's different depending on the environment you grew up in. And so the peak stays the same. The tails of the bell curve can be compressed or they can be flattened out further depending on each individual person, their anatomy, and the physiology of their capability of hearing. It does change over time. Obviously, younger people tend to hear better than older people. I like to say my husband has the capability of turning his on and off, but that's not always the case for everyone. But certainly that is the typical range. It's a bell-shaped curve, and our spike is between 2,000 and 4,000 hertz. The global glass standards and the methods. So we just learned how to get data and why we get data in the areas of 80 hertz to 5,000 hertz. But what do you do with that glass transmission curve, loss curve, once you have it? Well, there's these standards. There's ASTM E413, which is the classification for rating sound, and we know it in the market as the STC number, sound transmission class. It gives you all the rules and regulations for taking the sound transmission curve, the curve we just saw right there, and applying rules and a contour to get a classification number. We'll briefly go over that one. The other one is ASTM E1332. This is the standard classification for rating outdoor-indoor sound attenuation. So we know that as OITC. And that is using the same exact curve, our same red dots there, but instead of contour fitting it, we actually do a weighted calculation that is concentrated on the lower end of the frequencies. And it's there to accommodate a calculation based on really traffic noises. And so OITC is one of the ratings. Of course, the ISO system, with their test method, they also have their own rating system, and that's ISO 717. And this gives you a weighted sound reduction number, and they abbreviate that as RW. Now, for most instances, again, they're using that same curve, and they're just applying their rules a little bit differently. And so on the next slide, I'll give you a little more explanation of what happens there. So for sound transmission loss, it is a contour fit. This is shown manually, but obviously it's done by computation. The teal line or the green line that you can see is very rigid. That is the contour. And that shape of the contour stays fixed. That does not change at all. What you do is you move that contour up and down on the graph to get the best fit for your sound transmission loss. And what you're looking at, let me see if I can find, there is no pointer on this, I don't think. Maybe you can see the pointer, I don't know. But what you're looking at is the change in difference between this rigid line and your sound transmission loss contour line. Once you get a fit that meets the rules, and the rules are, you can't have any points below that teal contour line that are greater than 8 decibels. So you can't fall too far below that line without a flag going up and saying, stop, you can't do the calculation anymore. So those bars at the bottom and that black line at the bottom help to show that 8 decibel rule. So if those black bars at the bottom tend to go up or over that horizontal bar, you know that you do not have a good fit. So all of those column bars have to be below the 8 decibel level. And then all of the dotted material under the teal line, between the teal line and the sound transmission class, each one of those points, as measured at each frequency, cannot total more than 32 deficiencies, meaning you can't have more than 32 spaces below that teal line, between the teal line to the sound transmission loss. Those are the 2 rules that are used for contour fitting. Once you get your contour set so that you satisfy both of those rules, and in this picture, you can see all of the column bars are below the horizontal 8 dB mark, and we have a sum of our deficiencies equal to 28. So we satisfy both those rules. Then what we do is we go from the 500 hertz mark, we draw a vertical line up until we meet the contour, not the sound transmission graph, but the contour. And then we go over, and that's how we assign the STC. Okay. So again, this is showing you manually how it would be done. It's done by calculator, obviously, today. So it's usually multiple functions that are run. You try to get the contour as high as possible with the highest fit possible so that you get the best STC number. But you do have to satisfy those two rules. The other part is if you put the contour too low, you don't have an accurate STC. So you could get that contour way below and have zero deficiencies, but then you certainly are not doing your product a favor. The outdoor indoor transmission class, as I said, is abbreviated as OITC. It uses the reported 1/3 octave band frequencies between 80 hertz and 4,000 hertz. It's used for outdoor and indoor noise rating, mostly traffic. It's not intended for environmental noises such as speech or the higher frequency. And you use the same stuff. The only thing I want to say about OITC is it does not discern well for glass products. If you look at the chart on the right, those are various glass products, and I apologize for it being as small as it is, but those are various glass products ranging from a 10 millimeter glass up through a double laminated insulated unit. The light gray bars are the STC values and how those change. The dark gray bars are the OITC values. And so what you can see is independent of the type of configuration, the OITC number doesn't change. And so it's a much more compressed number, very, very hard to discern between the products. Okay. And this is just a summary chart for comparison of those single number ratings. It tells you the abbreviation, a description of what it is, what frequencies are taken into account for it. So you can see STC starts at 125 hertz, where OITC starts lower at 80 hertz. STC goes up to 4,000 hertz as well. Okay. And so you can see that there are some definitely differences. There are some downfalls to the rating. The current single number systems fail to differentiate glazing performance adequately. Many different configurations can come in with the same rating, yet the space between that contour for STC could be in different spots, and therefore the noise that you're hearing could be different depending on its origination. STL at all frequencies isn't used. So even if you run 80 to 5,000, you're not necessarily using all of those frequencies. The perception difference at the same performance level as what I was talking about, you can have two units that have an STC of 45, and where the dip below the contour is could be different for both of them. And so in your application, one is better, could be better than the other. None of the systems incorporate a baseline. So you can't say, oh, compared to 3 millimeter glass or 1/8 inch glass, this is what my performance is like. And so that you don't ever have that grounding mechanism for them. You also don't get any benefit for performing above the contour. So if you have a very highly performing acoustic material that the best fit because of those decibel numbers shows that most of your graph is above that contour, you do not account for it. And so that might be right in the critical area where you need the performance to be. And most of the time, non-acousticians have no idea what these numbers mean. They're just see a number on a specification and say, meet that. And so that is, those are some of the current rating downfalls. And there are some things that can be done to help, spread knowledge and get that better understood, but it is a fairly complex mechanism. So leaving the test methods, and so the key I want you to take away from that is 2 rooms, stick something in the middle, blast it on one side and see how quiet it is on the other side. And that's how you get your values. But then let's go into what you can do with glass design. So there's levers that you can use to get sound reduction. Glass mass is the biggest one. So you can go to thicker glass. Thinner glass has higher sound transmission than thicker glass does. The key to remember is that the critical frequency, remember that frequency where the sound goes through easily. that moves lower with the thicker glass, not higher, right? So the thicker you have the glass, the critical frequency tends to move to the lower hertz regions. So if you're trying to block out something that is happening, noise that's happening at 1600 hertz, you don't want to use 8 mm glass because that's right where the critical frequency is. You're better off actually using 4 mm glass because you actually have more performance there. And so those are some of the critical things that you need to think about when you're using those types of glasses. The other lever is the gap. So we can change the gap. It's most effective in insulating units with a 1/2 inch or 12 mm airspace or greater. You do get to a point where the airspace is so great that you have to do other things in design if you're going over a few inches. But for the most part, somewhere between a 1/2 inch and an inch is very, very effective. The overall single number rating is rarely enhanced with glass infill. We get this question all the time, meaning if I put argon in there or I put krypton in there, is it going to change my overall rating? And the answer is no. And the reason for that is you gain some at certain frequencies and you lose some at other frequencies, but the overall rating ends up not changing. So this is another one of those instances where if you are very, very specific about what you need to put in, you would have to run a test with the amount of gas infill that you need. But overall, the overall single number rating doesn't change when you change from air to argon to krypton. There are some gases that certainly do make a difference, but they are very, very rarely used. And then you get greater damping benefits when you combine air gap with laminated glass. And so obviously you keep making the glass thicker. And then you have our last lever, which is the interlayer. And what the interlayer does is it allows for damping. It can be used in combination with airspace, with thicker glass, double laminated, all of those types of things. And it contributes to the system by giving you that hand on the tuning fork or grabbing the bell and just damping that sound so that it doesn't come through at the same intensity. And that's what the interlayers do. The most typical configurations for laminated glass in acoustic, you can start with a single unit laminated glass, which is 2 or more pieces of glass with an interlayer in between. You can go up to a laminated insulating unit, a double laminated insulating unit, triple, where one or all 3 of the constructions of the glass layers is laminated, and then even into the multiply laminated for high-end security or other controls. And so those are the typical laminated glass configurations you'll see utilized for acoustics. The interlayers themselves have undergone an incredible evolution since we first started testing for acoustics in the early 1960s. And I liken it to the telephone. So we went from the telephone, the old telephone that some people don't even remember at this point. I'm dating myself here. The old rotary phone was conventional PVB. And I say that because you know what? It worked really well. You could accomplish what you needed to do. It still works really well. If you find one of these old phones and you plug it in, you can still make phone calls. You might not be able to dial out today, but you certainly can accept phone calls on it. But then it moved to a more engineered product, which is a monolithic acoustic PVB, where it was engineered to have greater sound damping. And I call that one of the earlier cell phones, the big clunky thing. Had some issues with that as from a processing standpoint. It was a little more difficult and wasn't all that production friendly. And then the big evolution over to the tri-layer acoustic PVB interlayers, or you could call them multi-component interlayers. And that's what we would call our cell phones today, where really, really highly engineered and highly functional and refined. And so what are these tri-layer acoustic interlayers? Well, they tend to have still between 2 pieces of glass, and they tend to be differing materials. In the case of the one we make, it is PVB skins, so your conventional PVB skin, with a highly engineered acoustic damping core. And that core is put together. Most people don't know, but your standard 30 thousandths or 030 PVB is the thickness of a credit card. And so this material is made in that same thickness. It's not thicker. It's actually the same thickness. It's made so that that core is the damping material. And it does create a much more efficient sound damping characteristic. And you can see that by looking at the evolution of the interlayers in sound transmission loss numbers. So the bottom black curve is 6mm glass, monolithic 6mm glass. You can see our lovely critical frequency there, right around 2500 hertz. And then if you look at conventional PVB interlayer, that's the bright green one. We had some advancement with the monolithic PVB interlayer, but then you can see that the tri-layer PVB material really did take care of that critical frequency curve, got rid of it, the dip, got rid of it completely, and really has brought up the amount of performance. A couple things to remember here is that a change in a frequency, in a critical frequency, or in any frequency for that matter, of 3 decibel units is barely perceptible to the human ear. A change of 5 decibel units, so that's from one of the solid lines up to the dashed line, that is very perceptible. So it is a noticeable change. And a change of decibels of 10 units or more is actually a halving or doubling of the sound, depending on what direction it goes. So in this case, you can see that the tri-layer acoustic interlayers actually can cut the sound by about 50% or cut it in half in the critical frequency range. So it's pretty good performance. What does that mean? Who cares, right? So what it does is it allows you to design systems in a much thinner overall capacity and get incredible acoustical performance out of it. And so what we did here is we looked for an STC. Both of these units have an STC of 44. We tried to find the closest OITC within that unit. So they're within 1 unit. And you can see that the material using conventional PVB, the overall thickness of that is quite wide. And by going to the acoustic interlay, we actually save 112 millimeters of space. And we can do that by just slight tweaking of the glass and using the acoustic interlayer. So you really can make much thinner units that have the same acoustic performance with these high acoustic performing materials. So they are really space savers. Laminated glass for acoustic control is something that we're seeing as an incredible trend. It's been used in windows since the 1960s. Most interlayers do tend to have a high inherent damping capability. So some are better than others. Some are engineered to be superior. Others just have a natural capability. Laminates do add to the flexibility of being able to tweak the performance. One of the beautiful things in the acoustical side is we do have the ability to change glass thicknesses, change air gaps, change all of that kind of stuff. Symmetry, asymmetrical, and all of that can be tweaked to give us different performance attributes. Remember that the critical frequency, the transmission loss, is dominated by the amount of damping. And so if you have a big dip right there, that you can put damping in there to help alleviate that critical frequency. You can increase your overall performance without going to thicker glasses and thicker units by putting the laminated glass in there for acoustical control. And you can have even higher performance with the tri-layer materials. And so one of the things that we do tell people is it is a polymer. All polymers tend to be sensitive to temperature. And so typically, and we recommend this for any type of laminated glass, but we typically recommend that the laminated glass be toward the interior for the most consistent performance because it can vary a little bit by temperature. Okay. Some design considerations for you are there is variability in the testing. So this is one unit. It's an insulating glass unit, laminated insulating glass unit, and it was tested at a single lab multiple times. It was sent to other labs, the exact same unit, and tested. And so you can see with the 6 tests that we did on this one unit, we have a variation in testing that comes out to an STC of 34 all the way up to 37. So keep in mind that this is one unit just tested differently or retested at the same lab in some cases, and you can get a plus or minus 3. Keep that in mind for specifications and for acceptance of materials, because that deviation could really change what you put in your system. What are some design considerations for glazing? What influences acoustics and what doesn't? So adequate damping and airspace of a 1/2 inch or more is recommended. Laminated glass with non-rigid interlayers. And so the rigid interlayers, if they're used by themselves, are not very good for acoustics. They are very similar to monolithic glass versus some of the conventional or the acoustically engineered materials. Thick glass should be used if you need very low frequency reduction, but remember our critical frequency also travels down, and so you want to pay attention to that. Using asymmetrical insulating glass constructions, symmetrical insulating glass constructions tend to be poorer in performance than some other constructions because the vibration is at the same frequency. Acoustic tri-layer interlayers give you some of the best performance versus the monolithic materials. The temperature of the glazing can have effect, and certainly the framing type. Now, so to this point, we haven't really talked about the framing type, but I'll give you the little tidbit and rule of thumb. If air can get through, well, then sound can get through. And so the frame type, the air tightness of the frame, and all of that have a big influence. Obviously, fixed windows will perform better than typically operational windows. What doesn't affect acoustics is the strength of glass, whether or not it has a glass coating on it, whether it has a pattern, a frit, anything like that, the glass color or the interlayer color, and again, the overall number, argon and krypton used in insulating glass units don't affect the single unit number. They can affect specific frequencies. Some factors in design, again, concern yourself with the use of the building. If it is going to be a school that's being built right next to a train track, you might want to have acoustical glazing in the school. If it is a greenhouse in the middle of a field that doesn't have anybody going in it except for once or twice a day, you may not need it. A hotel sitting right on a highway, yes, those types of things. Understand the type and origin of the noise. That is very critical. If you have low rumbling noise, you're going to want to concentrate on a higher OITC number and look at where your frequency is coming from. If you have higher pitch noise, you're going to want to look more at stuff above 1,000 hertz and what's going on there. Also, how frequent your noise is, because you could have a lot of noise when there's nobody in the building and it be quiet during the day. And so those are some of the things as well. And also your windows and your glass cannot make up for poor wall construction. So if the sound is stopped going through the windows but comes right through the wall, your occupant will not be very happy. And that's not much we can do about it, but those products should be closely matched in order to get the optimum performance out of them. Again, the type of window or system, fixed versus operable, those do make a big difference. The window dimensions, again, very large windows and very small windows, we have to concern ourselves with edge effects and vibration and damping. So in some cases, very, very large windows can give you more of a whoomp, whoomp, whoomp sound if they get moving and vibrating. Where little windows can sometimes give you a hissing sound because they're so stiff and the air is like whistling through. Installation quality, obviously we don't want air getting through, because as I said, if air can get through, sound can get through, the air infiltration rates, and then the critical frequency of the entire system, because you can't rely on just one component, and you can't take a poor frame and put a very, very high performing glass in and expect it to perform at any level higher than that poor frame, and vice versa. You can't take a super engineered and acoustically sound frame and put in low rated glass and expect that frame to make the difference. It's going to go to the lowest common frequency. Some applications that use sound a lot, certainly airports, and you can see this is one in Barcelona, one in Austria, that uses a ton of laminated glass to help the acoustic side. Some school systems and educational facilities to help with the learning and the environment, bringing the daylighting in, the natural aspects of it, the liberal use of glass, the multifunctionality of incorporating color and with the natural daylight. Some hotels and spas where you're looking for natural beauty, serenity, the exotic looks where you can incorporate color and whatnot. You want to make sure that you have the sound and comfort there. Hospitals, many different aspects of the hospitals, but the facades, but also the interior applications for divider walls for health and cleanliness. Glass, as we all know, is very easy to clean. And so all of that really does incorporate the use of acoustic glazing, especially with the HIPAA laws and things like that. Certainly that transfer sound from one room to the other or from outside to inside is critically important. Offices, we did talk about all the production and concentration and focus and all of that type of stuff. So offices are incorporating laminated glass in their facades and also in their interior partitions for the comfort of sound, but also bringing daylighting further and further into the building. So those are applications. And mixed use. A lot of times, you have these materials where you have stores and whatnot below, and you have residences up above. And that's one of those time of the day type thing. It might be very loud during the day. Some cases it might be louder at night, and you have people trying to live and run their lives up in the upper floors. So those are also applications for acoustic glazing. Museums, of course, museums tend to be quiet and serene, and they want you to focus on the art that they are displaying or providing, and not be distracted by the outside noise or the poker run that's going on with the motorcycles outside or whatever happens to be happening. So that's a application. And cultural facilities where thought, prayer, and concentration and relaxation are also very, very critical. We also see sound reduction applications in government buildings where we have multifunctional needs for wayfinding and for security. And incorporating laminated glass for acoustics is a natural for things like that. And sports arenas as well, the facade and the VIP boxes, which, by the way, I've never understood. If you're going to a sporting event, maybe I'm just jealous, but you're going to a sporting event and you don't want to hear what's going on outside. So I'm very confused about that one, but we do see a lot of those VIP booths being glazed with acoustic glazing. And I'm often told that the reason for that is those booths are used when there's non-sporting events for other meetings and things like that as well. And so that's why they do that. And I'm just joking. Obviously, I understand why they're putting that in. And one, concert halls. Nobody wants to go to a concert hall, and especially an opera or a show or something like that, and be distracted by outside noise and what's going on. The other part, as I alluded to, is you build your building and you don't know what's going to get built around it. And so a lot of times we look at, well, let's just put a product in that just meets the code, that just is going to qualify us for everything. And then voila, we end up having a world built around us, and the building occupants are not happy. The building use is not comfortable. So we do try to encourage people to think a little bit further and put it in at the original building, and anticipate the growth and the environment and people living around the building, because you cannot move the building. Unlike a car that you can drive down the street and go to a different place, you can't move the building very easily. So the last thing I wanted to hit on for you is the link. Remember at the very beginning, I said we have liberal use of glass, and glass tends to be the weak link, or traditionally has been the weak link. Well, let's just look at just a tidbit of information out of the industry. Is it really the weak link? So we have a concrete wall, and that concrete wall is 4 inches thick. That will give you, according to the National Concrete Manufacturers Association, an STC of 40 if it's hollow and a 48 if it's solid. Pretty impressive. Well, remember, we're looking at the glass being the weak link. Well, that's 4 inches thick. Laminated glass with acoustic interlayer at 5/8 of an inch gives you an STC of 40. A double laminated insulated glass at 1.5 inches thick gives you an STC of 48. I think it's time our industry goes through some paradigm shifts. Glass as a weak link is no longer an excuse not to use glass in a building. Use acoustic glazing and you can get the performance you need. You don't need to have large cavities to have acoustic performance. You can standardize the cavities as long as the configuration that you put together is correct. You don't need custom frames because the glass can fit in more traditional frames, so common systems can be used. Thick interlayers don't necessarily need to be used anymore. You can use standard offerings. One of the things that I didn't mention in this presentation is that a 030 acoustic tri-layer material, interlayer, will give you better performance than 090 conventional material. So you don't even have to go through the thicker interlayers. And then the complex specifications, if you desire multifunction, you can get that performance today by using these products. So in summary, acoustic damping is what you're looking for. You enhance comfort and versus non-laminated glazings. It's used effectively in a single unit all the way up through a triple laminated or a multi-ply system. The tri-layer acoustic interlayer is an engineered product specifically for sound control. It does bring multifunction to the products. It can be placed in one or more lights, and you're able to design into new and even existing structures and retrofit in with it. So you can enhance your spaces through the use of acoustic glazing. The benefits for architects are you increase the noise damping without increased glass thickness and weight. You have the ability to increase daylight openings without compromising or sacrificing acoustic comfort in your facilities. You can provide acoustic comfort when buildings go up in less than ideal locations because the land and the real estate just isn't available in an ideal location. These materials are safety compliant to ANSI, CPSC, and the European norms. You have a lot of design flexibility because they can be combined with colored interlayers, colored glass, coatings, patterns, all of that kind of stuff. So you really do have the multifunctional aspect of it, and you also have the ease of cleaning, which is a nice, easy wipe down and very important in this day and age to be able to clean surfaces that are non-porous. So that is the end of it. At this point, I would like to open this up to any questions. I know Sarah has been monitoring the chat as we go. So Sarah, is there anything anybody wanted to know while we went through this?
Yes, thank you. In fact, we have quite a few questions. So if we're not able to address yours, Julia's email is on the screen, so please take note of that, and you can also contact her directly if we don't address it live. First question, can you comment on the decibel rating and how it seems to match STC ratings? Are they the same thing?
So the decibel rating is the actual rating at the frequency. So when you push the noise from one side of the room through the sample to the other side of the room, they record that at a frequency. And so the decibel is the tag that's put on that sound pressure. The STC is a rating of all of those sound transmission losses. So it isn't the same number. The STC really is a rating and the decibel is a performance number.
Okay, great. Next question, apart from laboratory testing, can there be on-site testing for acoustic performance?
Yes, so I don't mention that because it does get quite complex, but you can do on-site testing. Many times you'll have acoustic engineers go out and they'll actually do a reading of your noise levels on your site before you even start building, so you get an idea of the noises that you're trying to you know avoid getting into your facility. But you can also do them inside the facility on site afterwards. There are some things that you have to remember, that you have a lot more variables coming into play where it's installed, it's in the wall. So you end up getting a composite number for the room versus a component number like we're sharing here.
Okay. Another question, if you're in a position of needing to compare products, what's the proper way to do that? Is it with a percentage or how do you calculate that?
I always like to say the best way, the single number ratings give you a rule of thumb, right? They guide you into a direction. So, if I have an STC of 33 or 35, they're going to be in that same ballpark. If you need to compare two units that come in at an STC of 33, the best way to look at it is to look at that transmission loss data per frequency. So that's where you'll use your decibel numbers. How much sound pressure got through at each of those 1/3 octave bands, and you would look at the area that you're looking to abate the sound and see which one has better sound transmission loss in that targeted frequency. So you really use the single number ratings as a guide to say, okay, I need to be in this range, but use the sound transmission loss graphs and those numbers to really hone in on the performance difference between the products.
Okay. Can you elaborate on STC and RW? Are they relatively the same?
Good question. So as you saw, they're both measured the same way. They have two rooms with a component in the middle. The biggest difference between the two, and I'll tell you that 99% of the time, STC and RW will be equivalent if it's not a monolithic piece of glass. Where there is a difference is the RW does not look for that 8 decibel spike or dip. So it only measures if there's 32 deficiencies under the curve. And so you could have a big giant dip in the RW value, in the frequency thing of the RW value, and it won't show up. And so where STC has two criteria you need to meet, the 32 decibel deficiency rule and the 8 dB at any one 1/3 octave band, RW only has the 32 deficiency rule. And so that's the only real big difference between the two. But some people feel it's significant enough where they don't like to use the RW.
Okay. Does acoustic performance reduce with lower PVB thickness?
Depending on which interlayer you're looking at. So conventional interlayer, it will reduce if you go from a 60 gauge to a 30 gauge to a 15 gauge. Yes. If you're looking at the tri-layer acoustic, it does not matter. Any thickness of that material will give you the same acoustic performance.
Okay. Is it easy to account for the effect of the frame?
No. There are rules of thumb that are used depending on what's going on, but usually the reason we test just the glass is obviously we make the inner layer and we want to understand what the inner layer is doing without a lot of outside variables. But we tend to tell people, depending on the quality of the frame and the type of window, you want to actually reduce it by, and this is just a rule of thumb, 3 to 5 STC units to get a prediction of what will happen in a frame. And so it's not rocket science, and it's not a hard rule. It's just to give some guidance.
Okay, great. I think we need to wrap up for the day. Again, if you asked a question that wasn't addressed live, we will follow up with you in email. We do want to call your attention if you enjoyed this topic and you would like to have more resources on it. We'd like to point you to NGA's Laminated Glazing Reference Manual. It was just republished in 2019 and has an informative section on acoustic glazing. While I posted a link in the chat to the downloadable version for sale, a hard copy is also available. In addition, we would appreciate your feedback on today's session, so I've also posted a feedback link in the chat. We hope to see you again on January 21st for the first of our 2021 Thirsty Thursday series, beginning the 4th year of these webinars. So we thank you for your regular support and attendance that has kept Thirsty Thursday an important offering to the industry. Julia, thank you again for your time and expertise sharing with us this afternoon.
Well, thank you very much for having me, and I wish everybody a very safe and wonderful holiday, and hopefully a very good 2021. Thanks for taking the time with me today.
Thank you. Well said. Good afternoon.
Bye-bye.